Okay, we're back, and we're looking at the relationship between the absolute value of the determinant and the area of the image and the original. So you remember that we've looked at shapes with their whether it be a circle or whether it be the unit square or something else. Those shapes have an area associated with them, those enclosed shapes. If we apply linear transformation to them, then those shapes change, and there is a connection between the area of the original shape and the image and the determinant of the matrix associated with the transformation. So we have here a transformation T, and what we can say is that the absolute value of the determinant of T is equal to the area of the image over the area of the original. So there's a ratio between the image area and the original area, and that ratio is equal to the absolute value of the determinant of T. Now, we've said earlier that the vertical lines don't refer to absolute value, but that's why we've got two sets of vertical lines shown there. That yes, the inner ones refer to the determinant of T, but the outer ones are actually, in this case, referring to the absolute value. So the positive value of the determinant, okay, is equal to the ratio of the area of the image to the area of the original. And so by rearranging this equation, we can say that the area of the image is equal to the absolute value of the determinant of the linear transformation multiplied by the area of the original. So let's have a look at an example. Find the area of the image of a square figure, side length of 3 units, when the transformation T, being given by this transformation here, 2x minus 3y, x plus 4y, is applied. So we're just going to rewrite this as a matrix, so it becomes 2, negative 3, 1, 4, just straight from the coefficients here. And so we can, from that, write the determinant of T, which is 2 times 4 minus negative 3 times 1, so 8 plus 3 is 11. So that's our determinant. The absolute value of the determinant obviously is going to be 11 as well. The area of the original, it's a square figure, side length 3 units, so the original area is 9 square units. Thus the area of the image will simply be 11 times 9, which is 99 square units. So after that transformation is applied, the new shape has this area. Okay, let's look at another example. We've got the figure here, which is a circle with the centre of the origin, x squared plus y squared equals 9, so its radius will be 3, and has a transformation applied to it such that x becomes 2x and y becomes 6y. Sketch the original and the image. Okay, so our original we know is a circle, radius of 3 units, centred at the origin. Now if we apply our transformation to that, then our new points, if you like, become here. So we've got x prime, our image of x is 2x, and so we can apply that to say 3, 0, and then so 2x times 3, or 2 times 3 becomes 6. Our y value we know becomes 6 times y, so 6 zeros are 0. Applying the same rules for x prime and y prime to 0, 3, we become 0 because 2 times 0 is 0 and 6 times 3 is 18. So these are two image points just taken from these 2 points here and here. Now you remember normally a circle after a linear transformation has been applied will become an ellipse, and so we would expect that to happen. So applying our simple rules to these main points, we get going to here 6, 18, and the same thing will work in the other directions. If we just think through that, 2 times negative 3 will be negative 6, and the 0 will still remain at 0, and the negative 3 here on the y becomes negative 18. Okay, so here's our sketch, and this is our ellipse. There's no need to go through anything more. We didn't need to do anything more, but we can see though the equation of the ellipse, remember, is x squared over a squared plus y squared over b squared equals 1 when it's centered at the origin. Okay, so 6 and 18 are our semi-major and semi-minor axes. Okay, so just worthwhile remembering that. Okay, just one of those things to commit to memory. Alright, so let's look then at applying this idea of the area and the determinant. The area of the image, you remember from before, is equal to the absolute value of the determinant times the area of the original. Now the area of the original we know is going to be pi r squared. Okay, so pi times 3 squared, or 9 pi. The determinant is going to be 2 times 6 is 12 minus 0, so it's 12. So the area of the ellipse, we don't need to go through any complicated formula to work out the area of the ellipse. We can just simply go 12 times the area of the original circle, which is 108 pi square units. So go back over that again if you need to, and we'll leave it there for this video.